Welcome back. In this episode, we push deeper into high-tech territory, constructing the research station, supported by a custom supercomputer, the High Performance Computing Array. And things get complicated fast. This is Star Technology. Let's get into it. So in the last episode, we managed to build the research station. So we've got the block. We can't do much with it because we need to build the other blocks. When it comes to building it, it's going to be a little tricky, a little bit more to it than I thought. There's a lot of blocks that go into it, obviously, because we've got the computer heat vents, computer casings, and the advanced computer casings. I'll come back to that later. Let's have a look at the multi-block. The research station is effectively like our scanner, the scanner that we're using to make the data sticks. This does the same thing, but for more complicated things, and it creates data orbs, these guys here. There's three key things that I want to point out here. So one of them is this thing called the object holder. So that's where we put the thing that we want to scan. It's got the controller block here as well, got the research station. And around the back is an interesting block we haven't seen before, which is this one, the computation data reception hatch. Research station itself doesn't have enough computing power to do research. So it's something that we have to provide externally. And we do that with optical fiber. The device that's responsible for doing the actual computing work is called a high performance computation array. That's another multi-block and it looks like this. So this is customizable. It's got energy hatch, fluid input because it can be actively cooled using coolant. It has this sort of array of heat vents on here, and on the other side, you can customize in this 3x3 grid what you actually want to have because there's components that go into it. So one's a passive heatsink, another one is a computation component which actually does the work. That requires cooling though, so you sort of have to have one of these and then a couple of these to do the cooling. As I said, you can have active cooling ones as well that require the coolant to be passed in. And there's actually a more advanced version of the computation component that we'll look at later. But essentially you build this, it's got a data transmission hatch. And so we hook up an optical fiber cable from here into the research station at the back there. And then that will give this computational power to do the research. Each one of these produces 4 units. I think initially we just want to do things that are about 8. And there's room for 3 in here. We could go up to 12, so we might as well do that. We'll have a bit of extra, which might make it go faster. So what's the first thing we want to research? Probably that ZPM energy hatch. So what's that going to require? 8. Okay, so that should be fine. But first we need all the components, and currently we only have the research station. What do we have? 14 of these computer heat vents, 23 of these advanced computer casings, and then 58 of those computer casings. So that's quite a lot. Let's get to it. So let's start with the computer heat vent. So this is what that looks like. Stainless steel frames, IV electric motors, stainless steel rotors, tiny stainless steel fluid pipes, copper plates, and samarium iron arsenic oxide wire. And that makes 2. And we're going to need 14. So have I encoded that recipe yet? I don't think I have. All right. So let's encode these recipes. Let's get the computer heat vent. It looks like I have everything except for that tiny stainless steel fluid pipe. So that shouldn't be too hard to do. Let's find out how to do that. Just in an extruder with a tiny pipe mold. Set up a recipe for this. So this is going to be a small problem. The tiny stainless steel fluid pipe, we don't actually have a spot to put it because we don't have any free spots in the extruder. So this is my extruder and every single thing is taken care of. I need to put another input bus, I guess. It's not pretty, but it will do. And using that, I can make rods and then bolts and then tiny pipe. Done. Put that in there. Now let's see if this works. Make 8, see how that goes. Yeah, I'd say that works. Awesome. All right, let's get back to this. So we were encoding the recipe for this. Now everything is in there. Cool. So I got the computer heat vent, put that into the assembler, put that into here. I'm going to need 14 of those. And that should work pretty quickly. A lot of stuff flying along. We've got some magnetic rods I can hear being made. Okay, all the parts are in there, but it's not making it. Why not? 1, 2, 2, 16, 16, 1. 1, 2, 2, 16. Ah, okay, we need 16 plates. Yeah, that's not going to work. Okay, let me fix that. 16 plates. put that back. I'll just take all these out. Cancel that craft and start again. Let's try that again. So make 14 of those. There we go. Done. Helps when the numbers are right. Okay, so what's next? After the computer heat vents, we need computer casings. So that's the recipe for these guys. So iridium frames, iridium plates, LUV circuits, fine cobalt wire, fine copper wire, vanadium gallium wire. Made in an LUV assembler, so we'll put it into the same machine. Let's encode that recipe. Done. Now let's check the numbers before we go any further. 32, 32, 2, 1. Okay, surprisingly that looks correct. Let's see if that is in fact correct. Those little mistakes with recipes are there to keep you on your toes, I feel. Okay, we need a lot of those. Computer casing. Why is there one already in there? Hang on a second. Have I already encoded that recipe? I might have encoded that recipe already. Check that out. Is it still there? It is. Okay, well, I didn't need to do that. Clear that. Where is that recipe? In the Elite Assembler 2. Oh, wait, does that need to be in a clean room or something? No. Okay, we need 58 of those. So let's order 57, because there's already one there. And next we have the advanced computer casings. So these require computer casings. ZPM circuits, fine cobalt wire, fine electrum wire, indium tin barium titanium cuprate wire, and that's it. So let's encode that recipe. Got all of those already, which is brilliant. And that needs to be made in a LUV assembler. So maybe I'll put that over here. And we need 23 of those. Let that go. What's the next thing we need? The object holder. That looks like this. It has a ZPM input bus, LUV emitter, a ZPM circuit, robot arms, electric motors, that uranium wire, optical pipes, soldering alloy, and polybenzimidazole, and research. So we actually can't make that because we've got to research it first. So we need a ZPM input bus. And then that also needs a ZPM input bus, so we might as well encode that recipe. That one. Done. Actually, while we're here, do we want to do the hatches as well? Fusion glass. Okay, that's cool. Let's just do the full works, because you never know when you're going to need them. Output bus and output hatch. So I'll order one of those. So that's going to take a little while. So in the meantime, I guess we can keep going. So the object holder looks like that. It's made in the assembly line, so I need to get rid of that data stick. Those numbers correct? It's 8 of those. There's only one of those. 2, 2, 16, 2. Okay, well, it looks correct for once. Encode that. Go over here. Now, I have built a second assembly line. I don't know if I've shown that on camera yet. As I was talking about in the last episode, it was becoming a problem with this hatch, because the next tier of data access hatch, which is the advanced data access hatch, actually requires the research station. So obviously that was out of our capabilities until we got the research station up and running. I can share the data sticks across the two machines. And I did do that thing where this makes the electric motors and this does the pistons and other things, so that way it can be doing them at the same time. But let us put this into here. So this will be the object holder. We had everything to make that. We're just waiting for the research so we can start making the object holder. We only need the one. And is that it then? No, because there's something called a computation data reception hatch we also need. So this is made in the assembler in the clean room from an LUV sensor, ZPM circuit, optical data reception hatch, and liquid polybenzimidazole. What's an optical data reception hatch? That is also made in the assembler in the clean room. Computer casing, LUV input bus, LUV circuits. Okay. Not too hard. So I'll encode that. That looks correct. And then I'll do this one. Yep. Cool. So I should be able to just pop these in here. Assembler in the clean room. Cool. Okay, so it looks like the input bus is ready. So let's scan that. So that'll be 2 minutes. So I'll come back. The advanced computer casings haven't started yet because the other ones were still finishing. All right, I'm gonna have to make more computer casings because the advanced computer casings are taking some of the computer casings, but that is fine. That is fine. We'll work around that. In the meantime, I could actually request that data hatch. Got everything for that? Yep. We're almost there. We're just basically waiting for that last thing, so I might come back when that's done. Got all the advanced computer casings. I've got the computer heat vents. Got the computation data reception hatch. Object holder is still going. The research station itself, and then the computer casings. And then I've got everything else. So I think I'm good to go once that object holder comes through. And then we've got to figure out where we're going to put this thing, because I don't have a good spot for it. I don't want to put it here. I want to put it out that way. Maybe, I think I might put it somewhere temporarily and then move it, because I am not happy with any of these locations at the moment. What we need it for is to make that energy hatch. We're going to use it going forward as well for more advanced stuff. But maybe for the moment we could stick it here and then move it later. It's not a big deal to deconstruct it and rebuild it. I'll just put it here. It's not pretty, but that's what I'll do. Is that even a good spot lined up with the... Oh, it's horrible. Oh, well. So we'll start with some heat vents. Put in some computer casings as well. The advanced computer casings through the middle. Now let's go underneath. Cover this up with computer casings. But then remember to put in those two extras. Over here, advanced computer casing, object holder, advanced computer casing, advanced computer casings, another advanced computer casing, the controller block, advanced computer casing, and then computer casings around that. Data reception hatch, LED energy hatch, auto maintenance hatch. Now we want some heat vents. More of these advanced computer casings. Then we fill this in. And then cover the last remaining blocks. Done. Whew, okay, that was difficult. That took a few goes. I've edited it so that you only see one of them, but that took a few times to get that right. Anyway, there we go. That's everything we need. So I guess we need to hook this up with some power and start thinking about the research we want to do. I don't like where it sits. It's pretty horrible. We'll find a better place for it later. I've built it 3 times now, so I'm getting pretty good at building it. Now that we have the research station, we're going to need to build some of these HPCAs, the high performance computing arrays. First, we're going to need to do some research. From the looks of it, we need a computer monitor. So how hard is it to make a computer monitor? Okay, not too bad. Let's see if I can encode that. We don't have glass panes. All right, I might have to set up a recipe for that. Cut a piece of glass. That seems like the easiest way. Although a casting mold for plates would also work. And we have liquid glass. Let's do that. That's a casting mold. No. Okay. No, hang on. I've got a fluid solidifier somewhere that does that, don't I? Maybe I don't. Okay, let's revise that idea. Glass dust in a casting mold. Oh, I'm gonna have to use the cutter. This is an LV recipe, so that's gonna be quick. So let's set this up. Over here, get this happening. That'll do. Computer monitor. Make one of those. Done. Okay, so I need to scan that. Oh, what? That's not what I meant to do. What is that? Displays data as a cover? How does that work? Wait a second, what was this? But it's just flickering. Is that decorative? I don't see any way of actually changing what it does. All right, anyway. Interesting to know. Scan that. So that will give us the ability to make the HPCA. Let's encode that recipe. Do we have everything in there? Looks like we do. ZPM assembly line. Oh, wait a second. What's that? PCB coolant. We do not have that. Okay. What is PCB coolant? Polychlorinated biphenyl and distilled water. Okay. What is polychlorinated biphenyl? Biphenyl dust in chlorine. Chemical reactor. Okay, what's biphenyl dust? Benzene and oxygen. Or benzene and toluene. Yeah, okay, benzene and oxygen seems to be the way to do that. Probably should set up a passive process for that, shouldn't I? I think we'll probably circle back to that. Let's keep going for now. Once we have that PCB coolant, that's pretty much done. So what else do we have here? We've got the heatsink component, computation component, empty component. Let's think about this. So the way it works is you need to have computation and you need to have cooling. Because we're just starting out, I think we'll just probably go with the simple one here, the HPCA computation component. That does 4 CWUs, which I think is computation work unit. Essentially what this machine is it's a server, basically, like a computer server. So you've got a casing around the outside and you've got this 3x3 grid in the middle. So with that in mind, we have 9 blocks that we can place. And given that each of these computation components requires 2 cooling, and each of these heatsink components provides 1 cooling, we're going to need a 1:2 ratio. So if we have 3 of these and 6 of these, that'll fill the 3x3 grid, and that will give us a total of 12 computation per tick. So yeah, okay. Well, I mean, that's the way to go, isn't it? We need to look at how do we make these heatsink components and how do we make computation components? What's involved in making a heatsink component? Made from an empty HPCA component, some aluminium plates, some stainless steel screws, and some PCB coolant. Okay, there's some more of that. In a clean room, HPCA computation component, empty component, ZPM circuit, LEV fuel generator, more coolant in a clean room. Okay, very similar. So what's the empty component look like then? Because that seems pretty common. Computer casing, IV circuit, data stick, PCB coolant, clean room. Okay. Yeah, these are not too difficult. This PCB coolant thing is cropping up all the time though. There's no avoiding it. We are going to have to create something that creates the PCB coolant. So I encoded some of those patterns, set them up. Basically, the only thing that's stopping us now is this PCB coolant. So we've got to get to that. Just a quick recap. We're using a chemical reactor on program circuit 1, reacting benzene with oxygen to produce biphenyl dust and water. The biphenyl dust will then be pushed into the next machine, where we will be reacting it with chlorine to make polychlorinated biphenyl and some hydrochloric acid. And then the polychlorinated biphenyl will be pushed into the next machine, which will be a mixer. And we will mix it with some distilled water to create PCB coolant, which we will put into a tank. So that's what we've got in front of us. Let's start by putting the machines down. Chemical reactors and in a mixer. Now, starting with the first chemical reactor, we are going to be making biphenyl dust. Benzene and oxygen coming in. That means that we can use an interface on the side here, I guess. Okay, so in here, we're going to want benzene and we're going to want oxygen. So set these amounts appropriately. We're going to want a pump on this side here. And we'll just say import. That should import both. Now the output from that is going to be biphenyl dust and water. So we can actually export the water back into the interface and that will get taken care of. And we can push the biphenyl dust into the next machine. So let's give that a try. I used the wrong oxygen. That's not great. Put the right oxygen in there. And this is empty Y, because I forgot to disable that button. There we go. Now we need program circuit 1. And the water is still there, but now it's gone. So the water should be disappearing through that interface. And the biphenyl dust is building up in there. Excellent. So next we want to make polychlorinated biphenyl. We can import some chlorine with an interface. And then we want a pump to import that. And there we go. Making the polychlorinated biphenyl and the hydrochloric acid. So we want the polychlorinated biphenyl to go into the next machine. So we're going to need a pump and a fluid filter. Actually, what I might do is just move this, because when I place this in here, it is going to start exporting immediately. And we don't want that because we want a fluid filter and we want to limit it to just the polychlorinated biphenyl. That should be right now. So if I pick this up, put this back, there we go. polychlorinated biphenyl is going into there. We need to do something with that hydrochloric acid. We could probably put another interface on the back, I guess. Let's do an import bus, because then we don't have to put a fluid filter on it. We import the hydrochloric acid and hook it up. So the hydrochloric acid should leave there shortly. There we go. Hydrochloric acid's gone in there because, well, Greg Tech. Get rid of that. And so now the polychlorinated biphenyl we need to mix with some distilled water. So let's get another interface. Put distilled water on that. We can just tell it to output into that tank. And now it's going in there. All right. So let's get a storage bus on that. Hook it up, partition it. So now we have PCB coolant building up. 1 bucket every second and a half because this takes 3 seconds. It produces 2. Now we should be able to request some of those HPCA things. This is the main one. That looks all good. Wow, there's a lot of components in that. Jeez. Okay, let's cue that up. See how that goes. So that's going to get built over here. I wonder if those numbers are correct. I guess we'll find out soon. Along with that, we're going to need some of these other things. So we're going to need 6 of these heat sinks. And 3 of these. Hopefully that works. I'm just going to let it do its thing. I'm not going to try and watch it. I don't know exactly where I'm going to make the permanent home for this, but one thing I do know is I would like to put the computation stuff underneath so that it's kind of hidden away. It's like the servers, so to speak, and then we hook it up with some data cable. So I guess we can just build it down here. How tall is this thing? 5 blocks tall. So that's, don't think that'll fit in there. Will it fit in there? 1, 2, 3, 4, 5. Yeah, it would be flush with it. Not ideal. I'll put it to the side somewhere. So the other things I needed to make was some computer casings, advanced computer casings, computer heat vents. We needed the data transmission hatch. Needed an auto maintenance hatch. It needs a fluid input hatch. Not that we're going to be using any in this particular one, but I think it does need it. I think that's everything we need. Maybe I will get the terminal to make this because it's a bit complicated. Just got to wait for all these parts. Once that's done, I'll come back and build this thing. I'm back. Because the system hates me, I had a few recipes that didn't work because they didn't have enough circuits in them, but I got through it in the end, and I have the high performance computation array controller. I'm going to use the terminal to build this because it seems a little bit complicated. I guess I'll just put it there and see what the terminal can do for me. Okay, that works. That's almost perfect, in fact. So I'll leave that open. Then everything else in the right spot. So I'll just move a few things around. Place that one that way. That. Same that one. Actually, can that be on the front? Because that would be better if that data transmission hatch was over here. If I can swap these two. I guess we'll find out. Now, we need to fill this. So my understanding, if it is correct, so I can put the computation components across the middle and then the heat sinks on either side. Hey, there we go. All right. Providing 12. Okay, that's cool. ZPM. Why is it ZPM? There's only an LUV energy hatch. That's weird. I only put in 1, didn't I? Okay. Okay. That seems to have like an idle. I think it's probably worth talking about this optical pipe because it works differently to wires and pipes that we're used to in GregTech. Even though it's called a normal optical pipe, you don't use a wrench to cut it or do the ends. You use a wire cutter. So if you're laying it out, it's just like any other existing wire or pipe. However, you can't create junctions. If I try and place it there, it does that. And if I use the wire cutter to try and join it, it won't do it because it's actually creating a T-junction. It can only be point to point. So it can't have any junctions at all. So I can't put a hole on the end there. I can cut that open there. If I put like 2 cables side by side, I can join them like that because that forms one single piece. But if this is just a little bit longer, then I can't join them anymore. Now that becomes important later when we want to hook up several of the servers or the HPCAs. We're going to need something that can actually handle multiple inputs and outputs. So there's a special device for that, but I'll talk about that when we come to it. There we go. Okay, well, let's scan this LEV energy hatch. So I guess pop that in there, and then the data orb goes in there. There we go. Well, it's going pretty quick. Let's quiet that down. Numbering on that is a little bit weird because that's not taking 400 seconds, is it? What's going on over here? Is this doing anything useful? Oh, there we go. Okay, that's cool. You click on these? No. Interesting. Okay. Oh, it's finished. Oh, there we go. ZPM energy hatch. Okay, let's put this over here in the assembler. Does that mean we can make a ZPM energy hatch now finally? No, hang on. Did I encode the recipe? No, okay. Let's put it in this one because this one's free. Okay, pretty sure we had all that stuff. I really hope I haven't missed anything at this point because I would be very disappointed. We don't need that because that's the data orb. Everything's there. Let me check the numbers. There's 4, there's only 1 of those. 2 coils, yep, okay. Let's put this in. And let's order a ZPM energy hatch. There we go. While that's waiting, let's have a quick look at what a 4 times hatch might look like. That one. It's making something. Oh, there we go. ZPM power. Oh, wow. Okay, we got to make a lot of those. Take that off. Can we just skip straight to the 16 amp hatch? Oh, no. Darmstadium. We don't have that. What about 4 amp? Oh, the 4 amp one's doable. Yep. What the heck is Darmstadium? Oh, yttrium barium cuprate. We'd have plenty of yttrium. Can we make yttrium barium cuprate? Yes. Yes, we can. That's not a problem at all. It's like RTM alloy coils and an MV alloy blast melter. But what is Darmstadium? Where do we get Darmstadium from? Probably, I think that's a liquid that comes from the fusion reactor. Arsenic and liquid ruthenium. Do we have arsenic? Hang on, let's have a look at arsenic quickly. I think we have arsenic. Yeah, we got a little bit of that. 277,000. This requires 200 million EU to start. And I think that means we can't do that with the fusion reactor Mark 1. Correct. 160 million EU. So we would have to go to the fusion reactor Mark 2. How hard is that? Okay, we can do that. We can scan this thing. Oh, no, wait. We need more computation. Dang it. We're close. We just need to get another one of those things. But then how do we hook them up? Oh, wait a sec. Okay, we'd need UV circuits. All right, we're not quite there yet. We can't get to 16 yet, but we can do 4. We can do 4. All right, let's do 4. I think it's funny that the standard hatch is made in a fancy machine using research, and then the 4 amp is just made in a normal assembler. Whoa, we already have all that. That's literally just a minor upgrade. LUV assembler. So I can put that over here and make some 4 amp hatches. So that's going to be equivalent to our 16 amp LUV hatches in terms of speed. So it's actually not much of an advantage at this point, unless I make 2. Actually, yeah, I don't know if it's going to help a lot. Let's try making one of those. I mean, it's important anyway. Let's do that. Then I need to decide what I'm going to upgrade. I'll have to figure it out, but we now have the 4 amp hatch. Awesome. All right, that's very exciting. Okay, well, I guess that's a good place to leave it. I am pretty excited that we got that hatch finally. That's been something we've been working towards for a few episodes now. Building the research station and then that high performance computing array and then that side quest with the PCB coolant, which I wasn't expecting, but you know, that sometimes happens. So what do we have on the cards for the next episode? Well, I think we're probably going to have to start working towards that fusion reactor Mark II. I want those 16 amp hatches, and I need some of that Darm Stadium if I'm going to continue. There's also the chemical plant. That could be interesting. I'll have to have a look into that. But yeah, certainly still loads of stuff ahead for us. Thanks for watching, and cheers.